This is the second Circle language video tutorial. There aren't many new features in Circle. It's mostly about rotating existing features into the compile time domain. But one new feature is the type enum. And this is like a normal enum in C or C++. It can be scoped or unscoped. It can have a fixed underlying type or not. But it carries an additional associated type for each enumerator. So if you give enumerators named A, B, and C, you can associate those with int, double, and string, for instance. And then you can retrieve the associated type through compiler intrinsics like enum underscore type or enum underscore count. So I'm going to go through a couple examples, and the first one is going to kind of look at the inspiration for the typed enum, which is the old C++ type list. So back in 2001, there was the famous Alexei Elendrescu book, Modern C++ Design, and it had some kind of wild metaprogramming ideas. I think one of them that really took hold was the type list, and that was a way to bundle multiple types together into a single data structure. The data structure that was used was a linked list, but it wasn't a linked list in memory. It wasn't a linked list at runtime. It was a structural linked list that used type defs as the edges between nodes. So if we were to program this old type list right here, and this was something that was produced in the Loki library that Alexandrescu had distributed with the book, and Boost MPL, the metaprogramming library. Boost HANA has a copy of it now, and then lots of people wrote their own. All right, so let's go through and create like a really simple type list to see what we're up against and what kind of improvements we can make in Circle. So each node in this linked list has two type defs. One is to the head, which should be a normal type, and then one is to the tail, which should be another list or a terminating type. So we're gonna do type defs here, and we're gonna define a special type that indicates the end of the list. So if you have a list and the tail points to NT, it references NT, then this is the last node in the list. Now we have to figure out how to like create new lists, and you're gonna do it through composition. So something like this. This would be a 3-element list. Now that's pretty horrible to type out every time. So of course, all the libraries would create a lot of macros. So a length 1 list is just this guy right here. So they all have to be terminated with NT. This isn't even correct. I failed that even. NT, here we go. Right, so this is a 1-element list. And then we're going to kind of use composition. So a 2-element list is a list with x0 in the head, and then the tail is a 1-element list. So we can carry this out for any number of elements. x1, x2, list t, x0, list 2. Let's do it for one last, just to be safe. Of course, in these libraries, there'd be 30 or 40 or 50 of these macros. And it really tortured the compiler because pre-C++ 11 compilers especially were not comfortable with as many template arguments. That looks good. Now, the question is how to do any operations on these, because they're not real linked lists in memory, so you can't like dereference pointers, you can't pointer chase. How to do any simple operation, we have to create templates, specialize the template on the list, and then use partial specialization to split up the nominal case from the tail case, or from the sentinel case. So the kind of simplest operation here is just to take the length of the list. So let's make a template class, list len t. And this is nominal, so this is for a list that has at least length 1. So we're going to create a compile time constant length, and we're going to set it to 1 plus the length of the tail. I think this is good. Okay, and then we have to be able to break out at some point. So if somebody passes an empty list being just the NT type, then we know that's a 0 length list. It's len t over nt, and this is going to be length 0. Okay. So now let's try this guy. So let's create let's say a list of length 3, and it'll have these types. We'll call it my list, and then we're going to just try to get the length of it. List len t. Let's see here, my list colon length, and let's print it out. This works at compile time, but we're just printing it at runtime. We could do it with a meta printf as well. Okay, let's see if this builds. Oh, nope. Undeclared identifier tail on line 20. Oh, I think we have a problem here. These type def never came through. Let's try again. String is not a member of namespace std. Okay. All right. Hopefully it'll print out 3. So we have a length 3 list. Now, this is really difficult to work with because we have to use partial template specialization to do any operation. So there's some that, finding the length or joining two lists that are pretty easy, but things like sorting, getting unique sets of lists is really very challenging and really torturous for the compiler. When C++11 came out, the parameter pack kind of replaced this linked list implementation. So it performed probably a little bit better, although I think it became even less intuitive on how to use it. So a lot of end users would just use like standard tuple, which has tuple size and tuple element, which are similarly defined template class templates to allow you to get pertinent information of each of the elements. But if you use like the Boost MPL parameter pack based type list or the stood tuple as a type list, you still aren't given the ability to iterate over individual elements because C++ doesn't have compile time imperative metaprogramming. It only has this difficult recursive pattern matching oriented template metaprogramming dialect. So these can be very useful, but they're hard to deal with, and Circle adds this capability to ordinary enums, which are very easy to deal with and which have a lot of dual and kind of ternary uses. So let's consider how to deal with a type list with Circle features. So to define a typed enum in Circle, you type enum and then you type name, and then you can optionally type class for a scoped enum. Give the name of your type. Then you can optionally put a colon and say short or long or whatever your underlying type is. So the only difference is for the declaration is you put type name right after enum. And now when we're inside, we're going to write the names of the types and optionally the names of the enumerators. So we can say a equals int, b equals double, c equals float. Or we can just put down the type without any name. And in this case, a name will be assigned that kind of follows the convention of underscore integer. So this is underscore 3 because this is the 0th, the 1st, the 2nd element. And so this would be a 3rd element. This is called underscore 4, etc. A, B, and C, because this is an unscoped enum, A, B, and C are going to be also declared in the enclosing scope, which is the global namespace. But this implicit declaration won't go into the enclosing scope. So it's as if this is a scoped enum for these two declarations. So let's deal without those for now. Let's just say int double character. Let's make 2 lists. Type this 2. Now, finding the length of this list is trivial. There's an enum count circle intrinsic, and that'll return you the number of enumerators. And because this is a typed enum, well, we know that these are the number of types as well. So this is essentially the length of the list if you were to use this enumeration as a list. But let's look at more complicated operations that are really difficult to do in C++ with the parameter pack implementation or with the regular linked list implementation. So let's try to join these two lists together into a new typed enum. So we'll call this join T. And we've got many weapons. So we can do like a compile time for loop over each of the type lists and declare new enumerators. But we also have this like intrinsic called enum types, which returns an unexpanded parameter pack with each of these enumerators in it. So this right here yields an unexpanded parameter pack with 3 elements, with an int, pointer to double, and a pointer to character. Now I can expand that pack and get all 3 of those elements as part of a list right here, initializer list. It's not really an initializer list, it's a enum specifier list. And we can do this for the second type list. Okay, so now join T is going to have 6 elements, right? It's going to have int, pointer to double, pointer to character, pointer to void, a 3 bounds int array, and a 32-bit character type. And if we want to print these out, we can use ordinary imperative loops. So here's an enum for loop. Printf. Okay. And let's give it a main function so it links. Let's build this guy. All right, so we have all 6 of the types in a single list, and we were able to join them just through parameter pack expansion. If you want to see the more manual way to do it, which is not any worse, and it gives you some more flexibility if you want to skip some or do more tests. So this would be enum count, type list 1, and then we would just use enum type to extract the ith type. So this is type list 1, I. And then let's do the same thing for enum 2. We have the same functionality. So you can use parameter packs, or you can use direct indexing with this enum type keyword. So let's go to the next level, and instead of just joining lists, let's join the lists and uniquify all the types. So if we've got redundant types, we just want one of each of them. This would require like sorting and unification. That's truly difficult to do with C++ template metaprogramming. It's probably possible, although it may cause compile times to go into the minutes or even hours, depending on the length of your input and how clever you are algorithmically. However, with Circle, because we can run any code at compile time, we can just pound include algorithm and use this, the quicksort implementation and the unique function to do all the work for us. So let's continue using some type lists and put more types in them. Let's get some redundant types just so we have more to uniquify. Okay, and let's call this unique. Let's add some more. Let's say put a double in there. Okay, now there's a lot to uniquify. So what we're going to do is create a vector of type mtype. So mtype is a 64-bit type that you're allowed to use at compile time that can hold any other type. So this is really an opaque pointer into the compiler's type information tables. And this lets us manipulate types as if they were variables. So we can use ordinary containers to hold types, and we can use ordinary functions to manipulate type lists. So we got to pound include vector now. All right. So I'm going to do pack expansion using the enum types trick. Type list 1. So this gives us an unexpanded parameter pack of types Now I want to run this through dynamic type, which will wrap it in an M type. So the result of this, the argument of this is a type, and the result of this is an M type. Now I'm going to parameter pack expand. I'm going to do this for the second list. So I can do this for as many lists as I want. Now we have a vector that is the concatenation of all these types. It'll be int, double star, double, character star, void star, star, etc. in a heap allocated std vector. So the next thing to do is create a unique set of types, because there's a lot of duplicates in here. We've got 2 of these character 32s, we have 2 of these int3s, we've got a couple of doubles, and so on. So let's create a unification function. We do it as a function template. Make unique. It'll take a L value reference to a vector. It'll sort the vector. It'll call unique on the vector. Begin. So the unique function puts all the unique elements in the front, and then it returns an iterator to the first non-unique element, which is going to give us the end of the array. So let's resize that input vector to the number of unique elements. Okay, this is like a stateful operation, so it's going to mutate this incoming vector and resize it downwards. So now we have a compile time std vector of M types, and we're going to call unique on it at compile time. All right, and now we're going to expand the types out from this vector in a parameter pack and expand that parameter pack. This is kind of the C++ 11 style way to do it, which is fine if you like parameter packs. So pack type returns unexpanded pack of types from a const M type array and a size count. So I don't actually have an overload for this to work with vectors yet. So you just pass it a pointer to the M types and the number of M types, and then it converts that into an unexpanded parameter packs and extracts the types out of the M type. So let's expand that out now, and this is a full-on unified type list. So we've just done a lot of like complicated metaprogramming work, and we did it all by using 2 functions in the algorithm header. All right, so let's give this some data and print it out. Okay, this looks good. Let's try to build it. Oh, and there we go. And what we have is a unique set of types. So we can add, let's say, a bunch more doubles in here, some character 32s, and run it again. And it hasn't changed because we haven't added anything unique. Now let's just for demonstration's sake, let's try the imperative way to declare a unified type list. So meta4 int I equals 0, I less than types dot size. Let's just do every other one. So we're going to skip every other type in the vector, and then we're going to use static type to pull the type out of the M type and then yield a type. So this yields a type, whereas this yields an M type, which is an expression. It's like a 64-bit PR value. And let's make it a pointer to whatever the underlying type is there. Okay, so this is going to be a little different. So this is doing some real like type manipulation. So we're going to pull out every other type from this list, and then we're going to create a pointer to it, and that'll be the associated type in this enumerator. All right. So we see we have fewer elements because we're only taking every other one. All right, so let's consider what we can do on a type list. And what often you want to do is use it to carry information around and then cause a dispatch. So I'll clear out the project here. Let's create a new type list, simple one. Enum type name, class type list t, I equals int, s equals string. Again, the names are optional, but sometimes really useful. So I'm going to create a function that can be called and given any one of these associated types. I'm just going to print that it's received it. Printf func called. So this doesn't know anything about the type list. It's just a function, and it's going to print its template argument out. Now I'm going to do the dispatch. So the dispatch is going to get any typed enum. Let's call this enum t. And of course we make a switch, and then of course we for loop. Let's see here, auto e2. So this is going to loop over all of the enumerators in the argument type. So if the argument type is type list t, it's going to make 5 iterations, 1 iteration for each of these associated types, or for each enumerator. So we're going to make a case from it, and then we're going to dispatch to our function template and pass it the associated type for each enum. Okay. Now let's try to call it at runtime, right? So at runtime, you're likely to have an enumeration value, which is, in this case, just an integer because there's no underlying type. So it'll default to integer. And it's just a 32-bit integer. You can pass it around like any other enum, but then you can use it to dispatch a template or function template. So let's set it to a string, which is s, right? And call dispatch. And let's see what happens. So we hopefully will see func of stood string called. Right? If we want to change this to F5, right? Func of array of size 5 of float called, right? And that's one way to dispatch. So we just generate a switch with cases for each of the enumerators, or we can use the special type name syntax in Circle and manually implement cases. And now instead of naming like the name of the enumerator, we're naming the underlying type or the associated type. This only works if the associated types are unique. But here it says, well, match this case when E's associated type is integer, right? So let's say, it's an int, the break, case, type name. What else do we have up here? Stood string. It's a string. Break. And I'm getting tired of typing, so let's say it's something else. Okay. It's something else because it's an F5. If we're to change this to be I, then it'll say it's an integer. There we go. So one thing that these type lists are really useful for is making discriminated unions, aka variant types. So a variant is just a union and an enumerator, or enumeration, and the enumeration indicates which of the slots of the union, which of the variant members is active. So let's define a variant here, and we're going to specialize it not over a parameter pack, but over a typed enum. So Circle provides an is typed enum intrinsic, and this will be true if the type is a typed enum and false otherwise. So this just gives us a nice error message. Must be typed enum. And now we're going to open up our, let's first put the enum in there. This is the kind of enum, and we're going to default initialize it. So let's declare an variant member for each enum type. And we're going to give it a name, and the name is the name of the corresponding enumerator. So this is going to take a string and convert it to an integer. And so now we need to get the name of the enumerator as a string, which is just enum name. So let's try an enumerator. Actually, this is scoped enumeration. D equals double. Okay, so if we specialize variant on my types T, we're going to get 3 variant members. We're going to get a variant member of type int called I, a variant member of type double called D, and a variant member of type pointer to const character called S. So by taking the time and naming our enumerators, we get to recycle the names and use those names for the variant members in the variant. So this is really nice because now we can say, like, this is the integer part, you know, this is the double part, and this is the string part. It helps with debugging and whatever else. So this is a flat data structure, and it has exactly the names that you specify. So let's try to do a visitor pattern on this. So we're going to try to unpack the data in the variant, the active member the active variant member in the data, and then pass that to a function. So the visitor pattern, again, is super easy. We're going to visit a functor. So this can't be a function, this has to be a type that has an overloaded operator call. The logical thing to do is a generic lambda, because a generic lambda looks like a function, but is actually a type with an overloaded operator parentheses. So that's what's going to be visited here. And a different template argument is going to be provided for each call depending on the active variant member. So again, we're going to switch over this enum, and we're going to switch over the kind. So this is the active variant member, and let's loop over all the enumerators. So you're going to make the case, and then we're going to call the functor with on one of these variant members. And so what is the variant member name? It's the identifier of the name of the enum. And that's it. So this is how we can visit. We can call a visitor function with the active variant member. So let's try to do something here at runtime. So variant t, my types t, var.kind equals, let's set the double member. And here's our lambda. See, it's generic. So this auto is like an implicit function template parameter. So we're gonna print out this type right here. And since we don't know what the name of this is, it's just this auto, which isn't a real name, we're gonna use decal type to get the type of the parameter out. So the decal type of the parameter is this type. Now we're going to print the parameter value. Let's make sure we have the IOStream included. Okay. Now let's visit. So it printed out. It called this into this function object with the function template argument of double, which is the type of the active variant member in the variant, and it prints out the active variant value, which is .d, which it got from the D case from this switch. So without any template metaprogramming, I wouldn't call this template metaprogramming really. This is just imperative metaprogramming. We're able to generate flat data structures holding type lists, use existing enum types, the plumbing for enums to carry type information, to carry the active variant member, because this is just a normal enum otherwise. And then we're able to generate an optimized switch that's completely flat. There's no recursion or anything else here to dispatch the active variant member to a visitor function. So this is a new data type in Circle, and Circle's not about creating new data types. It's about creating functionality at compile time. But I put this in because it's one that reuses existing mechanisms and allows you to exploit information that the compiler already maintains for you. So a lot of the introspection, like enum name, enum count, that's information that's always been maintained by all compilers. But they didn't make it accessible because without compile time control flow and without compile time imperative execution, there's not much you can do with it. But once you add, once you add a metaphor or a meta expression statement, this already existing but latent type information becomes really valuable. So that's why I exposed a lot of intrinsics to get at those, and then it was only one step further to create an associated, to maintain an associated type for each enumerator. And so this can replace type lists. It can replace parameter packs. Like this is a variant without a parameter pack. Not only does it not have a parameter pack, it allows you to name externally. It allows you to name the variant, each of the variant members. So also we've seen from the previous examples that it's really trivial to go between parameter packs and a typed enum just by expanding the parameter pack, and then you can go the other way. You can go from a typed enum to a parameter pack by using the enum types intrinsic. So this would give you an unexpanded pack, and you can do whatever manipulation you want with it and then expand it out again. All right, I'll have more video demos soon. Thank you.